Hello and welcome to today's webinar, Geological and Hydrogeological Considerations for Achieving Water Cutoff in Rock, Which Grout to Use, When and Why. My name is Jessica Williams and I'm the Marketing Manager here at Avanti, and I will be playing host and moderator for today's event. But before we get started, I want to remind each of you that there is a questions function in the GoToWebinar panel. We're going to have a Q&A at the end of this hour, and feel free to input any questions you think of through the next 45, 50 minutes of content, and we'll get to as many questions as we can at the end of this. So now I'm going to let our speakers for the day introduce themselves. So Brad.
Hey, thanks, Jessica. My name is Brad Crenshaw. I'm General Manager for Ground Engineering Contractors. We're a geotechnical contracting firm out of Tennessee. We primarily focus just on grouting applications. I've been grouting for about 20 years in the mining and heavy civil industries. So that's pretty much my background. Britt?
Thank you, Brad. Thank you, Jessica. Yeah, my name is Britt Babcock. I'm the president with Avanti International and have been for a couple of years now, but I've been with Avanti and in the grouting industry for 10 years and was a practicing geotechnical engineer for 12. So I've got over 25 plus years in and around construction, and appreciate the opportunity to present this webinar to everyone. So thank you.
All right, great. Thanks, Brad. Thanks, Britt. Before we get started into the main presentation, we're going to keep it engaged. So first, we're going to have a poll question, and it's launched now. How often do you use grouting in your projects? Always, usually, sometimes, never. We'll give it about 30 seconds. We just keep these poll questions intertwined in the presentation just to keep it engaged. So answers are coming in, and we'll share these responses when they're done. All right, just a few more seconds, collecting responses. All right. Okay, and as you can see, sharing the results, 52% say sometimes, so that's great. So now I will give this presentation to Britt to get started.
All right, thank you, Jessica. So let's start with really defining what is an injection grout. Well, what it is a liquid resin that can turn into an impermeable solid in a particular time frame. That can be a cementitious type grout, it can be a urethane type grout, or it can be an acrylic type grout. What are the goals for injection grouting? Believe it or not, there are a multitude of different applications in which grouting gets used for controlling groundwater, stabilizing soil and rock. When we boil it down to what the real goal is, it's just those two items. It is stabilizing soil and rock or controlling groundwater. So where are grouts used? Like I said earlier, a multitude of situations. We'll just name about a dozen or so here. One of the frequently used situations is in assets collections or mainline sewers, laterals, and manholes for controlling infiltration into those systems on a small scale. For soil stabilization, you can see in this particular photograph, these sands have been stabilized using cementitious grouts, which allows for the sands to stay vertical and still support the foundation above. They're also used in hazardous waste containment, whether it's hazardous waste or an environmental waste that's been used to contain those particular items. It also gets used in subways and tunnels, whether it's an existing subway system for maintenance and controlling infiltration. Water is definitely a thing of life for us. We need it to survive, but it's also a thing of nuisance and can wreak havoc on our below ground construction components. And so they also get used in tunnels and for controlling groundwater infiltration as well. Mines, tunnels, slopes, and shafts, water control in those situations. It also gets, injection grouts also get used in concrete and earthen dams. Also beneath structures for soil foundation, solidification, and soil improvement, as well as in break-in, break-out for tunnel boring machines in the shafts, along with the tunneling, mining, and the TBM's advancement. Grouts can be used either behind in the precast units or in advance of for controlling any kind of groundwater inflow or strengthening the soil components. Grouts get used in pre-excavation dewatering situations. This particular situation, they controlled a tremendous amount of water inflow, 25,000 gallons per minute down to less than 25 gallons per minute. And you can see that the injections were done very close and very safely to an existing river. But today's focus is on geotechnical grouting and more specifically rock fractures and things of that nature. So let's get into, again, I mentioned early on what the primary grout types are. And there are 3 primary grout types, 2 predominant, 1 less used frequently, but still noteworthy. The first is cementitious grouts, or also called particle grouts. That contains ordinary Portland cements, whether it's a type 1, type 2, or a type 3. Also the ultrafine cements. And ultrafines can be comprised of microfines, ultrafines, or superfines, and we'll dive into that here in a little bit. And there's solution grouts, also known as the chemical grouts. And within that family of grouts, you have the polyurethane grouts, or the hydrophilics and hydrophobic foams. And you also have the chemically reactive, which are the acrylamides, the acrylates, the acrylics, or the sodium silicates. And last but not least, and not used as often, but definitely noteworthy, are the asphalt grouts, or the asphalt grout called bitumen. So starting off with cement and cementitious grouts, to give an idea of sort of the different scale of micron size, the average micron size for, let's say, a Portland cement type 3 is roughly 15 to 20 microns. And what distinguishes that difference to, let's say, a microfine or an ultrafine or a superfine is its particle size. Microfines typically on average have 8 micron particle sizes, whereas ultrafines are on average 3 microns. Superfines is average is 1.5 microns. Why is that important? Or let me put that into scale, a reference for you. Your average human hair is about 70 microns. So if you think of the ultrafine cement of only 3 microns, this little dot there, take 3 of those, and that's about the size of an ultrafine cement in comparison to the diameter of your own human hair. Here's an example of sand column test. This was done at our plant in Malad City, Idaho. But these are also replicated and done at the Colorado School of Mines annually at their different grout schools, as well as the one down in Phoenix, where they actually inject grout up into sands. And you'll see here where ultrafine cement was injected into this 6-foot column, and it actually went the full height of the column, whereas an ordinary Portland cement only went about 20 inches. So driving factor in that is particle size of that particular material. Also plays a role with surfactants and or superplasticizers as well. But just to give you a scale of the penetrability of the finer particles. Here's in a rock fracture situation where these very, very fine fissures and cracks have actually been injected with ultrafine cement. The black is what represents that, just to give you a perspective in what that might look like in a rock fracture situation. What composes an ultrafine cement? You're going to have a Portland cement and along with a pozzolan. Generally, those are the 2 components. Of course, when you're mixing, you're also going to have a superplasticizer. You'll have water. And there are other admixtures that can be used, like whaling gum or diatom gum, depending on specific mix criteria. But the general components, the core components of an ultrafine cement are Portland cement and a pozzolan. What type of pozzolans are typically used? Slag is one of the pozzolans that's used predominantly in the industry. A lot of slag-based ultrafines out there. The coal fly ash, silica fume, and VCAS are not used very often, almost rarely anymore, but slag is definitely one of the man-made components. For natural pozzolans out there, it's pumice. Pumice is used, and from a natural perspective, metakaolin, calcined clay, and diatomaceous earth, although albeit they could be used. We almost never see them in the ultrafine cements anymore, but just definitely noteworthy in that regard. So moving on to our solution grouts and the subfamily of polyurethane grouts. These consist of the hydrophilic foams. Hydrophilic foams have a strong affinity for water. They typically are single component and they react with water, whereas the hydrophobic foams have a little or no affinity for water. Excuse me for a second. They'll have a base resin with an accelerator, or also known as a catalyst, and a little bit of water can react to that reaction. And sometimes they're 1-to-1 mixed ratios as well, component A to component B. Viscosities of the polyurethane grouts, regardless of whether it's a hydrophilic or hydrophobic, can range from 35 to 50 centipoise on the low end to as high as 3,000 centipoise on the high end. Reaction times can be a few seconds to as high as 30 to 45 seconds, or a minute or two, depending on what the temperature may be. They're definitely sensitive to temperature and the reaction times. But a little bit about the hydrophilic foams. They are a TDI, or toluene disocyanate based material. They can form a gel, a foam, or a solid. Like I said earlier, they're single component. They can react with water. Tend to have moderate expansion and are flexible, which is great because when we're doing localized grouting, which is predominantly what urethane foams are used for, in flexible situations allows those components to move and still maintain water resistance or water impermeability. They are harder to accelerate, but there are potable water approvals and they have a fair chemical resistance. The next generation that was developed after the hydrophilics were the hydrophobic foams, and they're an MDI based, or methane disocyanate. They can foam a foam or a solid. They tend to be higher in expansion, anywhere from 20, 30, 40 times expansion. They can either be direct dual component, or they can be a resin with a catalyst, like I said earlier, or an accelerator. They have a wider range of consistencies, with flexible to semi-rigid to rigid. They can be accelerated with their catalyst. They have potable water approvals and good chemical resistance. So that's a snapshot of the urethane foams. Jumping into the chemically reactive grouts, they comprise, again, of the acrylamides, the acrylics, acrylates, and silicates. They are a two-component A and B system. The viscosities are generally very, very low, ultra low for the acrylamide and acrylics, low for the acrylates and silicates. Basically, they can permeate anywhere water can travel, and they have controllable set times. The acrylamides and acrylates up to 10 hours. I've actually seen them go longer than that. Silicates about an hour. Two-component system, just a quick snapshot of what that might look like. You have a component A plus component B. Mix those two together and you'll form a gel in a controllable time. So more specifically about the chemical reactive grouts, acrylamides, they were invented in the mid-20th century. They're an organic-based material. They're non-structural, so they're flexible in nature with no tensile strength, so predominantly used for water control. Again, low viscosity, long design lives and long set times. They do have a manageable toxic component. They're handled safely on a regular basis, and once cured, it's inert, non-toxic, and irreversible. What's interesting is AV100, chemical grout by Avanti, in a cured state actually meets potable water component criteria. We've tested it. The grout is not potable certified. I want to emphasize that, but it has been tested against it, interestingly enough. We were curious how that would test, and it tested very, very well and passed. Moving on to the acrylates, they were invented in the 1980s. They're an organic based as well, also flexible in nature, so used in water control. Slightly higher viscosity because the prepolymerase chains of the acrylamides to create the acrylates at 3 to 4 centipoise. Shorter to medium design life. They too can be controlled out to as far as 10 hours. And they generally are considered a non-toxic component. They're right on the threshold, but oftentimes have just a slight component of acrylamide base to it. Sodium silicates, also considered water glass. They're inorganic in nature. First used in the 1800s, by most considered temporary. That can be anywhere from 2 to 10 years. They have a consistent, reliable, repeatable compressive strength component, so often used for excavation support and underpinning. They can be susceptible to syneresis, that is the extrusion of water after it's gelled over time, and generally have a shorter set time of up to about an hour. for controllable factors. And last but not least, we talked about asphalt, or bitumen is what it's called. It's a high volume water control material, high viscosity, typically high flows, high viscosity, and it's very durable and can be improved by addition of a binder. Oftentimes it's used as a fast moving water situation, and it's forced down into the formation and creates an immediate plug, because the second water hits it, it stiffens and can really slow down fast moving water. So, and Jessica, I'll hand it back to you.
Okay, great. Thanks, Britt. So now we'll launch poll question number 2. It should be up on your screen. Question: which grout type do you use most often? Cementitious, chemically activated, polyurethane, asphalt, bitumen, or none? Give it about another 15 or 20 seconds. There's about half of the votes in. All right, we'll close it out and share the results. So 63% say cementitious, 21% polyurethanes, and 10% none. Interesting. All right, now I will let Britt take back over.
All right, thank you, Jessica. That's about what I would expect, that cementitious would be the predominant grout used, and we'll talk about that here during this next slide series. I'm going to do about a 100,000 foot view of which grout to use when and where, and then Brad is going to get more in depth about the design issues and or design practices and approaches for grouting rock fractures and things of that nature. So the two types of grouting, we've talked about the types of materials, the types of grouts, but the two types of grouting also fall into 2 categories. That's penetration grouting or rock fracture grouting, or permeation grouting or soils grouting. Again, this presentation is on predominantly rock fracture grouting. So that's basically the grouting of fractures or other geological features that can accept grout. We categorize crack injection and void fill into this category as well, although that's more localized for urethane, but still applicable. And then permeation soils, we'll just do 100 mile-an-hour blow-by a mention of the soils towards the end of my section here, but soil permeation grouting is sands and gravels. Also a phenomenon that happens in a rock formation called matrix porosity. We put it under permeation because it's grouted like a permeation perspective or permeation job. So what are the grout types typically used for penetration grouting? Ordinary Portland cement is going to be the first and foremost. We just saw that in the poll probably. And that's why it's probably used 95% of the time in all grouting applications for 2 reasons. One, the geology will accept it. And secondly, from a cost perspective, once the geology may tighten, we oftentimes shift to an ultrafine cement. And in some situations like matrix porosity, a solution grout would be used. So what's the controlling factors for that? Well, aperture width really is, right? The width of this aperture is going to tell me how big of particles I can get into that aperture. And Brad's going to go into detail on that. And of course, matrix porosity, if your project or geology has that phenomena, it's going to be interesting. And Brad's going to talk about that in detail as well. Quick rule of thumb, greater than 120 micron in size, you're going to be able to get an ordinary Portland cement in there. And then as the fractures tighten, you may drop down into an ultrafine cement around 12 microns or somewhere in that range. And of course, if you are in a matrix porosity, more than likely, and not always, but most likely, you're going to have to jump into a solution grout or a chemically reactive grout like an AB100 acrylamide. What are the typical grouts and how are they used again? Like I just said, the Portland cements, most jobs start with a Portland cement. For 2 reasons, again, cost and the geology's willingness to take it. And then you may jump into a microfine or an ultrafine. If Portland won't go in, you're going to have to move to that in order to get penetration into that rock fracture formation. Again, asphalt, where is it used? It's used in the care of moving water in large openings. It's a type of grout that if you have large volume water and you need to stop it quickly, and you need something to not move with the water and create a plug. Asphalt's a great solution for that situation. It's been used in that situation often. Polyurethanes are also used in the case of moving water, but they're just from a sheer cost and volume perspective, they're typically only used in localized grouting applications for the most part. If you've got a large volume, large area, more than likely you're going to go to one of the other ordinary Portland cements, ultrafine cement, or a chemically reactive if it's the right application. Again, chemically reactive, they're used for very small fractures or matrix porosity. Acrylamides and acrylates are long-term applications or fine void fill opening sizes. Sodium silicates, again, are considered temporary or non-permanent by most in the industry. Now, if we were to look at the different aperture sizes and increasing flow for in situ, where we might use these types of grouts, this is just a quick chart. The upper limit of the chart talks about aperture size. Larger aperture size, you're going to get the Portland cements, the low mobility grouts, the polyurethanes, and the asphalt. But as sizes start to get finer and finer as we move down to the right side of the scale, you're going to drop into the ultrafines, the sodium silicates. And as you get into matrix porosities, you may put in an acrylate or the acrylamides, so the colloidal silicates. I mentioned we're going to talk about permeation grouting just in general. Permeation grouting, now we're talking about the grouting of sands and gravels and or matrix porosity, but more specifically sands and gravels. What are the type of grouts that get used in that? Well, any one of them, right? Depending on the application. That's why I say basically all grouts can be used in permeation grouting. That really can be clear as mud, but don't let this dissuade you. We actually are going to have a follow-up webinar in 3 weeks from this one. We're focusing on rock fractures here. The next one we're going to have is going to be on soil permeation grouting. We'll get more into the specifics on that as we get closer. But just as a teaser, some of the 3 factors that fall into play with permeation soil grouting are grain size, fines content, and permeability. But yeah, more on the next one. Thank you.
All right, thank you, Britt. So here's our third and final poll question, and after this, we'll jump into Brad's section in this presentation. So this is an easy one, yes or no. Have you ever had to use multiple grout types on a job? Give it about 20 seconds. Got a little over half. All right, just a few more seconds. All right. So fairly close. 58% have said yes, and 42% have said no. All right, so now we are going to move this presentation over to Brad, so you have control.
Okay, thanks, Jessica. Unfortunately, for some reason, I cannot see anything on my computer now. Can you tell if that's on my end or your end?
I believe it's on your end. I can still see. I am happy to move controls if you.
Okay, well, I'll keep working on it here, but I'll probably remember most of it enough. So the first thing that we're going to be talking about is we're just going to kind of run through some theoretical calculations on what grout can do and how it goes into the formation. So the first slide that we should see will be one that is showing the groutability ratio. And this was developed in the early 90s, I believe, by Weaver. And what it does is basically for a particulate grout, which is going to be a cementitious grout, then we can calculate what size fracture that will go into. And the old rule of thumb in grouting is that the grout will go into a fracture which is somewhere between 3 to 6 times the maximum grain size of the grout. And this formula pretty much follows that. So you'll see that the groutability, which is defined in the criteria below by a ratio of between of above 5 being continually groutable, and below 5 or below 2 being not groutable, and between 2 and 5. Oh, I got it. Came back up, so we're good. I don't have to make up stuff anymore. Within the range of 2 to 5 being possibly groutable, then that basically follows into that criteria that the rule of thumb that we talked about between a fracture between 3 to 6 times the diameter being groutable. But anyway, so what it means, if you look at the calculation here, then the groutability ratio is equal to the width of a fissure, so that's the fracture in the rock, divided by the D95 particle size of the grout. So basically, that's about the largest grain size of the grout on average. So that being said, I went ahead and put together some slides here, here we go, chart here to give an idea of what is groutable with our typical types of particulate grouts. So a type 1 or a type 2 Portland cement, which are equal in grain size, are listed at the top. And depending on the literature that you look at, the D95 grain size varies. Actually, your Portland cements, the grain size is based off of what's known as Blaine fineness. So the grain size curve is not standardized. But if you look at most of the literature and what the vendors will provide you, then for a type 1 Portland cement, you're typically looking at this D95 number here. So going back to that equation on the previous slide, then that is equal to about a 0.23 to 0.7 millimeter fracture that is consistently groutable. So depending on exactly which grain size you have, you should count on grouting up that fracture size. So trying to give people an idea of about what that is equal to, that's about the thickness of the plastic in like a Coke bottle, or a plastic Coke bottle, just to give you an idea. Type 3 Portland cement has a D95 that typically ranges from about 30 to 100 microns. So there, running that same calculation, you're at about 0.15 to about 0.5 millimeters. Well, that is about the thickness of a 8 to 10 pound test fishing line. So, if you go bass fishing or trout fishing, or probably not trout, but salmon fishing, that's about what you're looking for. So, a fish in the range of 5 to 15 pounds is what you're looking at catching. Finally, ultrafine, then it has a D95 in the range of 8 to 12 microns. So the calculation results in a groutable fracture width of about 0.04 to 0.05 millimeters. And that's about the thickness of the plastic that comes on your bread bag, not the thick 12 grain bread bag that my wife likes to buy, but the bread bag for cheap white bread that you make a bologna sandwich with. So that gives you an idea of the type of sizes that or type of fractures that the grout can go into. That being said, we also can kind of get a general idea of how far the grout will travel in a fracture once it makes it into it. So first, you got to get the grout in the fracture. Once it's in the fracture, you need to push it along the fracture. So there was an equation developed by Lombardi which is presented there. And I'm not going to go through the equation, but what I am going to talk about are the parameters associated with it. And you can see that essentially the length that you can, the distance is the length of the channel, the distance that you can push the grout is based off the pressure that you push it with, the radius of the channel, which is going to, for our purposes, be the thickness, the aperture of the fracture, and the cohesion of the grout. Another factor that generally you'll hear about it and plays into it is viscosity of the grout. Viscosity of the grout controls how fast you can pump the grout into the formation. So it's an important factor, but we don't go into that here, but it is something to consider. So viscosity is important also, but the parameters that we're looking at here are essentially pressure, fracture thickness, and cohesion. So another chart, just to give you kind of an idea of what we're looking at, how far grout can travel. So basically we took those same types of cementitious material, and we're looking at how far they can travel. We're keeping cohesion standard, so we chose 8 Pascal. Depending on your theory of grouts, all grouts that we use with a mixture of cement and water and additives are going to be somewhere between, say, 1 or less than 1 Pascal up to maybe 28 to 32 Pascal max. And depending on how you look at this, then 8 Pascal may be a thicker grout, it may be a thinner grout, just depending. But we're going to use it. It seems pretty reasonable. And we'll choose a pressure of 100 PSI, which is about what we would be using at 100 foot of depth in North American grouting applications. So that being said, if we look at the top one or the top 2 Portlands that we talked about previously, and we choose sort of the average minimum fracture size from our groutability equation, then we would be able to push that grout a distance of about 70 feet theoretically. And so, I know most people can figure that, but just trying to throw some ideas out there, that's a little bit shorter than Niagara Falls. So I didn't do a metric conversion, but maybe if you're from a neighbor from north of the border, then you can do that conversion in your head. Top 3, Portland, average fracture rate, minimum fracture diameter that you would expect to penetrate would be about 0.35 millimeters. So that calculation works out to a length of channel that you're going to push of about 50 feet. So if you figure that a diameter of travel from the hole again, then that's about the length of a basketball court, which is about 94 feet. So again, pretty good distance. The ultrafine, you're looking at a fracture, about an average fracture width of penetrable diameter of about 0.045 millimeters. So the length of that channel that you could do would be about 6 foot. So if you figure that based off of double it for a diameter, then you're looking about 2 people high. Might not be quite 6 foot, but close enough. I told the state of Tennessee that I was on my driver's license, and they accepted that, so I can claim that here. Those are just to give you sort of a idea of the length that you can push a particulate grout in that situation. Just a little bit of discussion here on a solution grout. Typically with a solution grout, you are going to be pushing through a much smaller aperture size. You can push those through essentially any aperture size. What it comes down to is how fast you can push those through that aperture. and that's based off the viscosity. So essentially, when you get into matrix porosity and very small fractures, you may have to go to a solution grout to get the grout to penetrate, and then depending on the size of those apertures and the hydraulic conductivity, then the viscosity is going to dictate whether or not you can economically push that grout into the ground. So based off of the information that we just went over, do we run calculations about what the grout is going to do for each job we do? No, we don't. It is not practical. And so the theory has been presented to try to give an idea of why we look at things a certain way, but you're probably never going to run those calculations. And one of the main reasons is simply because you'll probably never have good information on the aperture width for a grouting job, which was the first equation, the groutability equation. I've been doing this for almost 20 years, and if I have any information on aperture width, it's generally something like large, small, 6 inches. It's not something that's really applicable to what we're doing as far as the calculation goes. I think the other really important thing to realize is those distances that were provided in the previous chart demonstrate that if a particulate grout will go into a feature, a fracture, then typically it's going to travel far enough to be effective. Most of the time, we kind of assume for grouting purposes that grout's going to travel about 10 feet, 8 to 10 feet. So we're very conservative on the distance that we assume that it's going to be travel. But as you can see, the calculations show that under the right conditions, it will travel a significant distance. That's not, you can't assume that it's going to do that under natural conditions, but you can see that a 8 or 10 foot travel distance is a conservative road to take. So what can we say when it comes to choosing the right type of grout based off of that? Is number one, sort of as Britt said, that some grouting jobs can be completed with type 1 or type 2 Portland cement for grouting purposes about the same. They'll fill the larger fractures, and that may be all that's needed. We assume that most jobs, and this is just sort of based off of experience in the grouting industry, can be completed with type 3 Portland cement. And that's for filling of fractures. And as you can see, you can get to a fairly small fracture size for filling and travel a fairly far away distance. And the other thing I think that we can reasonably assume is that if we don't get the results that we need, then either it's because we are looking for a higher degree of cutoff than is the typical industry standard, or we have conditions that are not typical of general geologic conditions. So we will look at, one more thing to go over quickly before we get into a couple of case studies is the Lugeon Unit. In case you're not familiar with the Lugeon Unit, Lugeon Unit is something that sort of corresponds to hydraulic conductivity, and it's used a lot in grouting, and I'll talk about it more, so it's probably important to have an understanding. But the equation for it is below. It's 1 liter of water taken per meter of test length per minute at 10 bar pressure. It's essentially can be sort of corresponded to hydraulic conductivity, which a lot of us are probably very used to. One Lugeon is very closely associated with 1.3 times 10 to the negative 5 centimeters per second. So that's a very close correlation there. Because they're not exact, then the correlation breaks down as you move away from that. But it's pretty good up to maybe 1 times 10 to the negative 3 down to 1 times 10 to the negative 7. I put this other column on here because to me this is a very interesting way of looking at hydraulic conductivity, and it kind of helps to wrap your brain around and explain things. But hydraulic conductivity is a velocity, and so we can think of it in terms of travel. And if you look at this, then under the test conditions, then you can see that a hydraulic conductivity of 1.3 times 10 to the negative 5 is equivalent to groundwater traveling about 13 feet per year. And it goes up from there and down from there. You can see. So it gives you an idea of sort of how far the conditions will allow water to move, at least prior to us changing them. Also, a lot of the times, and especially Lugeon does a better value of predicting this than hydraulic conductivity does. But you can kind of get an idea of what type of grout you may be looking at. So this is just a rule of thumb, nothing definitive, but over on the side, I've listed sort of what you may be thinking of based off of a Lugeon or hydraulic conductivity unit. So two examples of where you may need to switch grout types on a job. Dam grouting jobs, I've listed one here that's in North Carolina called Northfork Dam. I'm not giving any particulars, and it's not so much specific to this dam, is just a general example because we've done this on a number of dam foundations. But most of your dam foundations are going to be done with a Portland cement grout. Some of them a type 1, often it's going to be a type 3. One thing about dam foundations, because you're not going to be doing any excavation and you have to generally prove this grouting to some regulatory agency, is that you're probably going to have a lot of water test data, and you're going to get a lot of Lugeon calculations, so you get a lot of feedback of what the ground is doing. And sometimes, and actually more often than not, you get into a situation where your Lugeon values from water testing do not necessarily match up with what you expect a grout take to be. So essentially, you get a high Lugeon value from water testing and a low grout take. And when that happens, oftentimes there's a scenario associated with it probably. This is, again, this is just a made-up example, but it demonstrates what's going on in the ground. On the right, in scenario 1, you have 10 fractures, which each has a Lugeon value of 10. So when you test this stage with a water test, you get a Lugeon value of 100. However, all of those fractures are too small to accept a type 3 Portland cement. Therefore, the other scenario that to compare it to would be this scenario over here, where you have the vertical borehole. You only have 2 fractures intercepting that borehole. They each have a Lugeon value of 50, so you get the same 100 Lugeon test value. However, both of those will accept Portland cement. So this hole takes grout, this hole does not, but they have the same values. likely what really happens on a lot of jobs is that you have scenario 1 essentially on the right side in red, where you have larger fractures that accept the Portland. Once those get grouted off, then you have the smaller fractures which do not accept the Portland, and because you need to get to a certain degree of water cutoff or a certain reduction in hydraulic conductivity on the project, then you may have to change grout types. And often, you take the next step down. So you were using type 3, you switch to the smaller particle size of a microfine, ultrafine, superfine, and that gets you to where you need to be to continue reducing the hydraulic conductivity of the rock mass. So on the Northfork Dam job, along with others, then that was sort of the situation that we're encountering. High Lugeon values with low grout, with low type 3 takes. A switch was made from the type 3 to an ultrafine, and that allowed for grout to be taken in higher order holes. Another situation that you may run into, it was a mining shaft that was in Kentucky. It was pre-excavation grouted with a lower mobility grout, so that was a sanded cement grout with a very high viscosity and a low or high cohesion. So it had a very low grout take. And during excavation, then significant inflow was encountered. And the mining GC started grouting with type 1 Portland cement grout, which most people have the capability of doing during the sinking of the shaft. The problem became that the water inflow was probably somewhere around 150 GPM. The Portland cement was able to cut that down to on the order of probably 70 to 80 GPM. However, at that point, no more Portland cement would go into the formation. So we got the call. We had them do some water testing, which indicated very high Lugeon values. So it seemed like grout should still be able to be taken, because if you remember our chart before, 300 Lugeons should be easily groutable by Portland cement. However, since it wasn't being done, then we ended up trying some microfine cement where there was no take, and ultimately had to go to acrylamide where we had a significant take. And this is one of the situations of matrix porosity, which Britt had discussed further. So if you look at these two pictures on the left, that is a 3D printout of a core that has 60% void space in it that's blown up some certain percentage. After we did the grouting in this rock, we realized that it actually had about 60% void space in it. So the rock in the right-hand picture is in the shaft wall. It has about as much open space as this picture here does. They're not of the same formation, but it's just to demonstrate what was going on. Ultimately, acrylamide had to be used, because even though there was this huge amount of void space in the rock, it was so small that a particulate grout could not be accepted. We may have been able to try some other alternatives and acrylate or even a sodium silicate. However, because of the problem of acceptance of other materials, we just immediately had to jump with our best chance of making it work. And ultimately, that grouting was able to reduce the inflow from about 60 GPM when we started down to about 5, which was able to be maintained during the grouting. So with that, I will turn it back over to Jessica.
Great. Thanks, Brad. So we've got about 10 minutes left on the webinar. We'll do a little Q&A session now. So we're looking through the questions that have come in, and Britt's going to help me field these. So Britt, do you want to go ahead with the first one?
Yeah. Thank you, Jessica. Great information, Brad. Thank you for sharing that with all of us, too. Brad, I'll let you field this first one, and it's on cohesion of grout. Basically, the question is how do we determine the cohesion of a grout? What is the testing method?
That's a great question. And I have actually this question myself. I am not aware, Britt, of a standard test for determining this that is at least routinely ran in the field. There's charts out there that have been published that can be provided, and I could provide the one that I'm referring to after this if necessary. But that being said, I really don't know of a test that the engineer or the contractor or whoever it is can do to determine it. My understanding is that it would have to be some sort of laboratory test that you're probably not going to do. So basically, yeah. But basically, my answer is I don't know.
Well, what you're saying is there are theoretical references or laboratory predetermined references that are available to compare to, and that's sufficient for the numbers you need in order to perform the proper calculations. When the calculations are actually performed, it's like you said, it's rarely ever done, or not every project. So. Yep.
And so I think we have the information to make general assessments. We really don't have a way to determine detailed analysis, but detailed analysis may not be important because we have general ranges we can use.
Yeah, great answer. All right, this next one is on balanced stabilized grouts versus unbalanced grouts. The question is, we've come across this from time to time, and what do you think is better and in what situation? Balanced stabilized or unbalanced? And I think it would help everyone on the. Yeah, I'm sorry. I'm gonna let you run with this one too. I think it would help if you defined a balanced stabilized grout for everyone on the call, just for those that may not know what that is, what that terminology means as well.
And this is very important. We could probably do another webinar on this. There's two trains of thought in the grouting industry. One is that you should be grouting with balanced stabilized grouts, and the other is that you should be grouting with unstable grouts. And I don't know if there's a specific criteria that designates one to the other. However, cohesion is an important part of this aspect. So a balanced stabilized grout, probably the two key aspects of that is that it is going to release less water. There's going to be less water pushed out under pressure. So the grout is going, the best way I can explain it is the grout is going to maintain more of a consistent viscosity and fluidity under pressure. That being said, the trade-off is that by definition, you're going to have a higher cohesion to a balanced stabilized grout. A non-balanced grout is going to expel more water under pressure. So essentially, it will once it gets pinched down in a fracture, then it is going to start losing water and become, let's call it, thicker. However, at the same, the advantage of those is that the cohesion is going to be much less. So your cohesion values for your unbalanced, unstabilized grouts are going to be in the less than 8 pascal range, whereas your balance stabilized grouts are going to be greater than 8 pascal. So at least you're going to get more penetration initially, at least with the unbalanced ones. Less penetration, but less change in fluidity in the balance stabilized grouts. I tried to make that as I tried not to get political in that answer because everybody believes strongly in what the type of grout that they do, but that's the technical explanation. And I would be not here, not the right place, but I would be happy to go into what I think is right and wrong if necessary.
Yeah. Well, you said another webinar. Sounds like we might have a fourth in play. You know, one of the aspects that falls into play that too is maybe mention what additives come into play. And I think Jessica, I know we're tough on time, so we may end on this one, but the additives that are typically used in a balanced stabilized grout, and then expand on that and discuss, Brad, if you would, because there is a question about bleed on unstabilized grouts. So expand on that. I think we're going to have to wrap up on this question. There's a whole slew of other questions, but we'll answer those with a follow-up, Doc. But
okay. So let me say first off, we need to be careful about what type of grout we're talking about, and if we're talking about low pressure grouting, so we're sort of talking about permeation grouting in shallow soils. That's going to be different than this rock grouting answer, because typically I'm thinking of rock grouting as deeper, 25 to 40 psi minimum. So bleed is something that really, in my opinion, we don't need to consider because we never inject grout under atmospheric pressure. Bleed is a measure under atmospheric pressure. So really pressure filtration is the important aspect of what we're looking at. And so this comes back to the question of, do you believe in balance stabilized grouts or non-stabilized grouts? Because non-stabilized grouts are going to filtrate. Balanced stabilized grouts are not. So that's my opinion on that. The additives, then again, you're looking mainly what you want to control. Both types of grouts want to control apparent viscosity. To do that, you're going to look at a super plasticizer. You're going to have a super plasticizer in either type of grout. When it comes to a balanced stabilized grout, you also want to reduce bleed, and you want to reduce pressure filtration. And so typically you're going to have some kind of gum and possibly a bentonite. So those two things are going to reduce that. Those are going to hold water into your grout. And so they are going to lower your pressure filtration and your bleed there. And those are your primary things that you're considering, I'd say.
Yeah, perfect. We're going to have to wrap it up there on questions. Jessica, I'll let you take back over. Thank you, Brad. Great answers.
Yeah, and thank you to the both of you. We've only got about a minute left. I just wanted to let everyone on the call know that we'll send a follow-up email, and it'll have presenter contact information as well as what we call promise documents, which is just a link to some more resources for you. And as Britt and Brad both mentioned, we will have another webinar specifically on permeation or soil grouting, and it is scheduled for Thursday, June 11th. Once that registration system is live, you will all receive an email notification. Other than that, thank you for joining us, and we'll look forward to having you at the next webinar.
All right. Thank you, Jessica. Thank you, everyone.
Thank you all.
Thank you.